And actually, dependency injection was one of the use cases we had in mind when working on this feature. And for those of you who haven't looked at dependency injection recently, let's just recap a little bit what we mean by this. So here, by dependency, we mean some kind of service that the component needs at runtime. And I've made two very simple examples. To the left, you have a C++ example of a function foo, which inside its implementation calls another function, getService, to get some object which it then will use. And obviously here you have a dependency that the function foo needs or depends on the getService function. To the right, you have a UML real-time example instead. So assume you have some optional capsule part called logger, which is typed by an abstract capsule, which has two concrete implementations, a simple logger and a timestamp logger. Then somewhere in your code, you have a call to the frame incarnate function where you specify this logger, and then you need to specify which concrete capsule implementation do I want to use for this capsule instance. And both these yellow highlighted things are examples of dependencies that you can have at various places in your application. And instead of hard coding the dependencies like I've done here, the idea with the dependency injection is that you specify the dependencies outside or in some central place, and then you inject them when you need them. And usually the object responsible or component responsible for this is called an injector object or a service locator object. And an injector typically has two responsibilities. One is to keep some kind of registry of all dependencies. So if you have an object A that depends on object B, then that dependency is managed by the injector. And then it's actually also responsible for doing the injection of the dependencies when required. So in this case, provide an object B to object A when it needs it. And when you read about dependency injection, you may get the impression that it only is applicable to objects, but it actually applies to all kinds of services needed by some client code. So you saw an example of a function here. It can be objects, it can be constants, threads. It can basically be anything that a component needs at runtime. And there are some benefits why people use dependency injection. One is to make it easier to unit test, because you can then mock out dependencies to be able to test a component in isolation without having all its dependencies in place. You can also use it for creating different configurations of an application. For example, the example I showed on the previous slide, where we have a logging system, two different implementations of it that we may want to switch between, and maybe you don't want to have that placed inside the code, but have it outside, maybe in some configuration file or something. Code can also become more reusable if the components are more loosely coupled. And in some cases, the logic for resolving a dependencies can be quite complex. And in that case, of course, it's good to centralize it. One example could be some kind of load balancing where you need to dynamically compute which thread a certain object should run in to optimize the overall application performance. And this is then good to have in one single place instead of having it in multiple places. So there are many frameworks already for C++ that implements dependency injection. Some are based on templates, so that it's not any runtime thing at all, but just something the compiler does. Some are based on runtime, but after doing some experiments with them, we thought it could be useful, at least for people not already using such a framework, to have a simple service in the TargetRTS that allows you to have dependency injection. And if we look at a capsule, it depends on many things at runtime for its execution. There are capsules that types its capsule parts. It also talks with other capsules through its ports. It has a thread that runs it. And maybe there is initialization data that you need when creating an instance of it, as we saw previously, etc. And we want to avoid spreading out such dependencies throughout the application and instead put them in some central place. And we introduced a new class in the TargetRTS, which we call the RT injector. It can be used for registering dependencies. Typically, you do this early, like in the top capsule constructor that runs at application's startup. In the picture here, you see how to use it. So you can access it calling get instance, and then there is one register create function, that registers a create function against a capsule part. And the capsule part is identified by its qualified path name, the same that is used in the model debugger. And then there is also a create function that actually creates the capsule instance, and then it takes those registered dependencies into account. Typically, you do this only once at startup, but it's actually also possible to dynamically change the registered dependencies at runtime if you need that flexibility. So let's take a look at this in another example here. So here is what the example I showed you in the picture before. So assume we have some capsule abstract logger, which has two concrete implementation, one simple logger and one timestamp logger, and we want to choose which one to use. So in our top capsule, we have one class pinger that just emits an event every second, and it's then sent to this log system in the logger capsule part. Inside that one, we have another capsule part, which is typed by this abstract capsule. So note, this was not possible to do before because fixed capsule parts couldn't be typed by abstract capsules, but now it's possible thanks to the support for custom capsule constructors and capsule factories. So then in our top capsule, we have created a constructor. And if we look here in the code view, we see that we are registering a dependency against this capsule part here. They happen to have the same name, but that was maybe just a bad example. But the first one is called logger, and then the second one also logger. And the create function we register looks like this. So to start with, let's use the simple logger actor. Just invoke it without any special arguments, just like that. And then let's build the transformation configuration. Building, let's see if we can find the console to run it. So I'm running this application now, and you see it just prints the ping message once per second. Also note that the logger and the top capsule runs in the same thread, so they have the same thread ID. Now let's change the dependency so that we instead will use the other implementation. So here I will comment this out and now use the timestamp logger capsule instead. And here I can use another thread that I have defined. So here I'm not using the default one that comes in as C, but I choose to run my logger in another thread. So let's save that and build the application again. Let's go here and run it. And now you see that the top capsule and logger runs in different threads, and also now we have a different implementation of our logging service that also prints a timestamp. So then to look a little bit on how this works then, I have created or added in my TC a global capsule factory. Here I've referenced in this property my own implementation of a capsule factory, which I have up here. And it's a really simple implementation. It will just override the create or implement the create like this. It will just delegate all create requests to the RT injector, and destroy it will just do as usual. And yeah, that's basically how it works. So then let's look finally at the slide summarizing the limitations that we have removed by implementing these features. So for fixed capsule parts, you can now run them in any thread you like. Previously, they could only be run in the same thread as the container capsule. You can type a fixed capsule part by an abstract capsule now. For capsule initialization, you can provide initialization data using custom capsule constructor, and this makes it possible to have reference variables in capsules, which was not possible before. Memory management we touched on, so by having a capsule factory, you can have full control over how they are created and destroyed, the capsule instances, like, for example, allocating them in some pre-allocated memory area. And last but not least, it's now possible to have template parameters for capsules. There are still some limitations here, in particular when you're trying to type capsule parts by template types, but at least you can use non-type template parameters like to specify constants like the size of ports or the size of a capsule part and similar things.